periodically, and these reseeds are shorter than it looks, because when you first look at the source code, it says 50 ticks. Now, you'd expect that 50 ticks are something like 50 times 100th of a second, but it's not. It's actually 50 millisec. And initially, when your system boots up, before it's getting fed entropy from security, the initial entropy comes from the system time, and it does just one reseed. So until security comes up, your random number generator is not strong. I'll leave it as an exercise to the listener to find things that get executed before security comes up and feeds entropy to the kernel. Okay, let's go to the next slide.
When looking through the kernel, which you can easily get from Apple, you get some really great quotes, and these three are excellent. They're really strange quotes. I like how they explain what an IV is, and then they go on to talk about how they don't want crackers to find their encryption patterns too easily, which I think is kind of funny. In addition, they also talk about how they don't lock memory pages in certain circumstances, but what's interesting is that we know that Apple actually doesn't lock memory pages in almost all circumstances. But here they just give an example of that. And curiously, they also have some problems where 192 and 256 magically just don't work. And they don't really say why that is. But that's interesting. So Maximilian Dornsiff, who I don't think is here, but it would be great if he was, he did some really excellent research on DMA attacks using FireWire. So pretty much anything that has a FireWire device is vulnerable to this, unless you either patch the kernel, or on PowerPC you can enable open firmware. At the Meta Lab in Vienna, Austria, there's a hacker by the name of Angelo Laub who gave a talk about how to secure against the FireWire DMA attacks. It turns out that on the Intel chipsets, you actually need to patch the kernel in order to fix this problem. He did that and provided the source code for doing that, along with a compiled kernel module, though I would probably compile it myself if I were you. And I linked that in the slides as well. But you should obviously be aware of this attack, and it is real, and it is probably possible that if someone's charging their iPod, they might also be dumping your memory if you have FireWire on your box. Again, I talked about this last year, which is the swap files and memory issues, which is basically you need encrypted swap to do disk crypto correctly. And until essentially 10.4, you didn't really have the option of encrypted swap, which basically meant that your passwords would get swapped out to the disk. Unhashed passwords would get swapped out to the disk. So basically no work whatsoever to recover the passwords. And so if, say, there was any type of exploit on your box, or if you have an airport card maybe in your box, I hear there might be some problems with the airport firmware and the drivers, you could possibly go ahead and look for keys that way too. So it's definitely something to keep in mind, and I don't know how the internal is actually, like the internals of this is actually implemented, but in loop.AES you have keys with the bits being shifted around so that you don't leave basically a trail in your memory. Peter Gutmann wrote a paper about this where if you have your key in memory for a long period of time, it oxidizes inside the memory cells. And I don't know if they do that or not, but it would be interesting if they opened this up so we could find out if they do. Because it seems like there are a number of things that if they've done that wrong, that could be another vector, though that's probably not a vector anyone here really cares about. But if you do, you probably aren't using this. As an example about how, I mean, everyone knows we need to encrypt our swap, right? But if you were to go to apple.com right now and go to /macOSX features file vault, they have a nice image on their page titled security, and you'll note the use secure virtual memory is unchecked, which is excellent. So apparently Apple, even when talking about security, neglects to mention that little problem. Something that I haven't heard anyone else talk about, Ralph and I were talking about this, and essentially if your laptop runs extremely low on power, you're going to have your memory contents written out to var VM sleep image. And it's careful, however,
it's not quite careful enough. So if you have encrypted swap on, the contents of the sleep image will be encrypted, but you're not actually asked for something like a passphrase when you boot up again. So what happens with the key? Well, guess what? They write it to the disk. So this is not really useful. I mean,
if you wanted to attack one of these laptops, not one of these, please, but if you wanted to attack one of these laptops, it would be possible to simply unplug and just wait. So obviously another vector here is weak passwords. So brute forcing is nothing special, though until a couple of days ago, neither of us had seen any brute forcing programs out there, other than I'd seen a bash script that someone used. They just wrapped it around HDI util, which is not particularly interesting. Then, was it like 4 days ago?
Yeah.
Ralph found actually brutedmg.c.
Yeah, that it's it's written by as of yet unknown person. Well, we have like a hint of who it might be, but so far he hasn't answered. And this is a program that allows you to brute force version 1 the images. So it will not work on the current FileVault images, but it will work on older versions. Like if you would be running 10.2 or something like that and had FileVault enabled, or actually, yeah, if you had encrypted disk images there, it would work on them, but not on the ones on Panther and App. So
yeah, so we mentioned previously that we had David up here, and he was able to implement about 200 keys a second running on his Sempron 3300, and that's kind of nice. I think previously we were getting about less than half of that.
Yeah. It was like 50 or 60 with the brute DMG.
Can you speak into the mic?
According to the brute DMG program, they were saying they were getting about 50 to 60 per second on their, I'm guessing their PowerBook or something, or MacBook Pro, something like that.
So David here is going to demo a program that he wrote in an amazingly short amount of time, and it's a vial fault crack. So if you want to give it a shot, we switch to his laptop, please.
It works. Okay. So yeah, the whole story behind this was that I met up with these guys a couple days ago when I just got into town, and they were explaining how all this stuff worked. And they mentioned that it uses PBKDF2, and the WPA cracking stuff that I have uses PBKDF2 as well. And so it just uses a higher amount of iterations. WPA uses 4096, and this uses 1000. So I was like, oh, I could just modify my FPGA stuff and get it to work really quickly. So I modified my FPGA stuff and implemented a cracker using their source code. And so I'm going to demo that right now. So right now you can just run VFCrack on your normal PC. And I just have this dictionary file, which just consists of a bunch of different passphrases that you want to try. And so all you do is give it the dictionary file and then whatever disk image that you have. And so this one's using the version 1, and it's going through at about 200 per second. And it should find it in a little bit. But all this is doing is just running the PBKDF2 and then checking the header to see if everything works properly. And so there, it just found the passphrase, which is 123456. And so I was like, wow, this is kind of cool. Let's see how fast it runs on the FPGA. So I have this shell script that swaps over the FPGA to the special image that I made. So this is reconfiguring the FPGA on my laptop, which is actually a compact flash card in my PCMCIA slot. And now it's running this code that is basically, the chip is accelerating PBKDF2 cracking. So now all I have to do is basically feed it over the same arguments and specify which FPGA I want to use, which is the only one that I have in my system. If I had multiple ones, I could use different dictionary files on the same DMG file on different FPGAs and split it up that way if I wanted to. But this one will just run on the one on my laptop. So right now it's going through at about 2,000 per second, and it just found it. So this, running on this little compact flash card, cracks this stuff about 10 times faster than a laptop. So if I had 10 laptops here, it would be about the same speed. This also works with the version 2 format, which I just got working about 5 minutes before this talk started. So here's a second image with the version 2. This has a different passphrase. Just running on my PC right now. And there, the passphrase is file fault. And then I can also run that on the FPGA and it does everything properly. So that's my portion, I guess. Yeah. Thanks a lot.
We could switch back to the other. Great. And of course, he did forget to mention that he has a cluster of 16 of these sitting on your desk or something?
Yeah, 15.
Yeah. Of the FPGAs, right? So that's a pretty excellent improvement over about 70 keys a second. So got some other references in here. If you happen to be the author of DMG Brute, it'd be nice to meet you, talk to you. And it's all going to go up on crypto.nsa.org/vilefault shortly. Actually, probably during questions, I'll copy it over. We'd like to thank these people for their help and for their input. So thank you all, especially to my lawyer, Jennifer Granick. Our lawyer, I guess. And every person at the EFF, thank you in advance. And everyone at the CCC. And also Club Mate. So now I guess is the time when we can take some questions, if anyone has any questions.
Okay, I'm sorry by advance because I'm gonna try to talk cryptography early in the morning. So it's just you didn't mention about the security of Firewall. You talked about I think you know about it, but you forgot to talk about the eventual weaknesses of the chaining mode, which is CBC, and I think there is some kinds of attacks on CBC. It was talked about a lot. In LoopOS or NDMcrypt some times ago. So yeah, you forgot about it, and maybe there is a reason, or I don't know, but I think there is some weaknesses on CBC which could lead as well to failure in Firewall.
Actually, using CBC is fine as long as you have a large enough block size. So the attacks that you usually have on CBC mode is that you have collisions, basically, that happen when you have small block sizes. Say you have DES and you have a 64-bit block size, then it wouldn't be a good idea to use CBC mode because you'd have a collision with a probability of 1 to the minus 32. However, for 128-bit block sizes, the probability of that happening is rather negligible. You could, of course, use other modes as well. I mean, one of the modes that you could use would be counter mode, but then you'd be kind of screwed because people could arbitrarily flip bits in your blocks, and you wouldn't know. So that's kind of a bad idea. The only thing that would, like, really improve the security over CBC would be to switch to something like the Disco